Hello developers, let's start developing. My name is Veko and this is the part 2 of task 21 for the 2021 Advent of Code puzzle contest, whatever. So, to recap the task a bit, we need to play a game, and in this game, whenever we roll a dice, the universe splits. So everything occurs simultaneously. We have a magical three-sided die that can roll 1, 2, or 3, and we roll it 3 times, and then we basically move that many times around the circle. Wherever we end up, that's how many points we get. So the game ends when either player's score reaches at least 21. First things first is that we are rolling the die 3 times. So basically there are 3 splits of the universes. On the first roll there are 3 splits, on the second roll, and there are 3 splits on the third roll, so that would mean that we have that many splits, 27 splits on each roll of the die. But come to think of it, do we actually split into 27 different universes? And the answer is no, because there are not 27 different outcomes that can come from rolling a three-sided die 3 times. So let's look at the options. So basically we are rolling the first die, and I'm gonna put 9 once, and then I'm gonna put 9 twos, 18 up to 27, and then 1 1 1 2 2 2 3 3 3, and then through the magic of copy and paste I will write this, and we can have 1 2 3 1 2 3 2 3, and let's copy this over. So these are all the possible outcomes that can happen when we are rolling a die. But what is their sum? So basically we can roll from 3 up to 9. And those are only 6 possibilities. There are not 27 possibilities. So instead of 27 equiprobable possibilities, we would have 6 possibilities that don't have the exact same probability, so to say. Because rolling a 3 is only possible if we roll 3 ones in a row. So that's only 1 out of the 27. And similar for rolling a 9, but we can roll 5 by rolling 2 2 1, we can roll a 5 by rolling 3 1 1, or by rolling 1 3 1. So those are multiple scenarios that are actually the same. So what I will try to do is basically separate these. So we can roll 3 in one way, we can roll 4 in 3 ways, yes. We can roll 5, let's group them here. And we can roll 6. And this is 6. Let's put the 7 over here. That's 6, that's a 7. Oh, we're moving those as well. That's a 6, that's a 7, that's an 8. Let's leave it here. That's a 5. Let's move this one low. That's a 6, that's a 7, that's a 6, that's a 7, that's an 8, 7, 6, 7, 6, 6, 6, 6, 6, 6, 6, 6, 6, 6, 6, 6, 6, 6, 6, 6, 6, 6, 6, 6, 6, 6, 6, 6, 6, 6, 6, 6, 6, 6, 6, 6, 6, 6, 6, 6, 6, 6, 6, 6, 6, 6, 6, 6, 6, 6, 6, 6, 6, 6, 6, 6, 6, 6, 6, 6, 6, 6, 6, 6, 6, 6, 6, 6, 6, 6, 6, 6, 6, 6, 6, 6, 6, 6, 6, 6, 6, 6, 6, 6, 6, 6, 6, 6, 6, 6, 6, 6, 6, 6, 6, 6, 6, 6, 6, 6, 6, 6, 6, 6, 6, 6, 6, 6, 6, 6, 6, 6, 6, 6, 6, 6, 6, 6, 6, 6, 6, 6, 6, 6, 6, 6, 6, and another 8 and a 9. You might have noticed that this has a certain symmetry. There is 1 9 and 1 3. There are 3 4s and 3 8s. There are 1 2 3 4 5 6 5s, and there will be, I guess, 6 7s, of course. And the middle one has the highest frequency because we have 3 6 7 ways to throw a 6. So we have one way to throw a 3, we have 3 ways to throw a 4, we have 6 ways to throw a 5, we have 7 ways to throw a 6, we have 6 ways to throw a 7, we have 3 ways to throw an 8, and only 1 way to throw a 9. And let's just check. The sum of these should be 27. Yes, those are the 27 possibilities. So this is the map of possibilities that our universe actually breaks down. So it doesn't break to 27 distinct possibilities, it breaks down into 3 and 3 and 1, 7 distinct possibilities. So that's better. Instead of raising something 27 to the power, we're raising 7 to that power. And let's just see 27, 7, and this is, yeah, just put in here the power. Up to 20. Let's see what, so it's this times e whole the 1. The 20th power, because the minimum, note that the minimum and the max, we cannot keep getting the same point value. Because the maximum move that we can move is 9. We cannot move 10. So all of these moves will basically be less than a full circle. In the first part, whether we threw 13 or through 33, it was the same because we will just run full circles. Basically, the tens digit doesn't do anything for us, or the hundreds or everything. We only care about the units. But here we will only throw numbers that are between 3 and 9. So what will be the minimum value of points that we can get? For the first, let's assume that, so if we start on 1, then the minimum number that we can throw, yeah, let's assume that we get the, let's evaluate, actually, not evaluate but estimate. We're gonna estimate what would be the minimum number of points that we can get. Let's say we threw a 1, and then we can only throw the minimum of 3, so that will be 4 points. And of course this will be, let's have it as sum of start of this up to this, and we're gonna log that in. So this will give us a sum of all the up to then. So we got a 4, and we are at position 4, and then we can of course throw, if we throw a 6 we'll come to 10, and we can throw a 7 and go to 1, so basically we can alternate between 1 and 4. So I think this is the minimum that we can, minimum amount of points, which means the game lasts as long as possible, and this would be the first, the third one, the third run, because our opponent will play as well, the 5th, 7, 9, 11, 13, 15, 17. So the maximum amount of turns that the game can take is 17-ish, let's call it. Of course, we can always throw and have a 9 on our first move, and then get an 8, and then get a 7, and this will already pop us over. So it can end as early as the 5th, move, but it can last as long as the 17, and that's the one that's interesting. Actually, the maximum number of moves that we can go. So for 20 moves, 17 moves. Okay, let's calculate 17 moves. That's 10 to the 24th power, and that's more than we can handle. Basically, anything above the 12th power is not really handleable in a real life scenario. But let's copy this over for 7. Let's see what we get with 7. And, well, this is borderline basically. So we might not have enough, so to say, memory or time or anything to calculate it. Up to 1 billion is doable, but anything larger than 1 billion makes me think. So, but let's try it. Let's see. So we have our table, we have our, so to say, analysis. And let's try writing some code. Check it once more that the thing is actually running. Yeah, we have 412344, and I will return to the one given in the task because we might have issues. We won't know if what we get is correct. 4 and 8. Just a second. Is this number too long? 3, 15 letters. It should be okay. But the reason I'm worrying is because of this. JavaScript is exact with numbers, meaning 1 plus 2 equals 3, only up to a certain point. This is the maximum safe integer. If I add 1 to this, I will get 2. If I add 100 to that, you can see that the number is not totally correct. So if I add 99 to that, it's gonna be something else. If I add 98 to that, it's 88, 97, 88, and so on and so forth. So that's the maximum integer where JavaScript basically guarantees that if you do integer operation, you will get a correct result. Above that, it's in the right ballpark. And let's see if this number is bigger or smaller. If it's smaller, we're screwed, but it's not. It's actually something like 20 times bigger. So we're fine. We should be fine unless we run into some overflows. So if we multiply this by something that's like 20, and 20 is not a huge number, we will run into unsafe territory. Anyway, let's try it. And this one is smaller than this one, we already checked. So how do we split the universes? And what? No, and we're not using 8 and 3. Just a second, that's what we got here. We are using 4 and 8. Yep. I'm thinking about how can we maybe describe a game. What is the state of a game? Well, we have the first player and we have the second player. And if we know their positions, let's not save bytes. And if we know their score, we basically don't care how this thing got to here. So what I mean is that if we have player 1 on position 1 with a score of 7 and player 2 on position 5 with a score of 8, let's say, the future of this game does not depend on the past. So we know everything we need to know about this game and we can calculate it moving forward. We need one more thing. We need to know who's next. Yep. So if we know, and we know that player 1 moves, so these are the 5 values that we need to actually continue the game, because this and these are branching out into different universes. But this doesn't matter how we got here. So okay. And I'm guessing we're gonna need a to key method, because I'm gonna want to have some kind of a dictionary for this. And let's just generate this. Yeah, it's a string when we are basically flattening out the array. And to key takes a state and returns a string. Okay. The initial state is first is next, and first has that position and a 0 score, and the second has that position and a 0 score. Yep, that is correct. And now we're gonna need to not create a puzzle, but we're gonna need to generate the universe. Next universes. So we're gonna get a game state and we're gonna return a game state array. And we're gonna return, actually what we could return is a mapping of a number to a state, how many states we get. Because now we can combine this with this. This is a constant. This is always. So if we have this state, we're basically, we can have any 6 of 7 of different next states. So one of these states will be the player rolls 3. So if the first player rolls 3, that means that he's on position 4, adding 4 points to his total, and the second person is next. That's that. The next one is that he rolls a 4, being on position 5, 5, 8, dot. And so on and so forth, so 6, 13, or 7, 14, or 8, 15, or 9, 16, and this is a constant. And we get one of these, and 3 of these, and 6 of these, and 7 of these, and 6 of these, and 3 of these. And oh, messed up somewhere. 3, this is, and 5 of these, and 6 of these, and 7 of these, and 6 of these, I guess. Oh, we were already on 1 and we rolled a number. So this is 3, 4, 5, 6, 7, 8. I messed up somewhere. 1, 3, 6, 7, 6, 3, and we're gonna have a single when it raised up to 17 points with this same thing. So how do we show this? Let's try with an interface and maybe we get lucky. So a next universe will have a multiplier that is a number, and it's gonna have the state, which is a game state. Yeah, that is a next universe, and this number shows us how many of those next universes we have, and this shows us the state. So this will return, let's call it a next universe array, an array of next universes. Let's write this out in a stupid way. Something like this, else. Yeah, so we're gonna need an array, and we're gonna need these multipliers, and the state will be yeah, one thing is for certain, the next will be second. The first we will need to calculate, but we know already the second. The second is state dot second. That's the same thing. Actually, let's have it as this so we don't mess up anything. Just decompose it, destructure it. And the first one will be, so we're getting, yeah, let's waste some space. The first will have what the position will be. Yeah, the position will be position plus 3. And let's take this and actually let's wrap it the other way around because I already got confused by it. And just put it here. Yeah, this will be one big long method. And I guess there is a better way to do this, but okay. So the first one will have its position increased by 3. And then taken modulo 10 or 10. Because we don't have a position 0, we have a position 10. and the score will need to be increased by exactly this number. Yeah, let's write that twice. It's not that big a deal, not that hard a calculation. I might need to eat my words later, but for now let's have it like that. Now let's have this as a thing, and this will be smart enough to actually copy over from below 8 and 3 and 9 and 1. And now we can just say that we actually want to map the universe frequencies to frequency to return this monstrosity. Is it that enough? No, it's not enough. We need this, and then we can have this and the multiplier. Oh, we can tuck that in once more. So the multiplier is the first element. You know what? I'm not gonna use a tuple, I prefer names. So this is the value and this is the frequency. And let's see if this is smart. Still nope. 7, 8, 9, and I will need to say that 4 has a frequency of 3, 6, 7, 6, 3, 1. Okay. So the multiplier is actually f dot frequency. And then when we're calculating, we actually need to add this is the f dot value and this is f dot value as well. No idea if this is right. It's gotten a bit convoluted, just the way when you're doing weird actions in Redux, you get to do something like that. So for the other thing, if the second is actually on move, next will be first. So first, second will be have this, but for the second, everything will be second, second, second. Yep. And first will be the deconstructed first. And of course, we're gonna exchange those two. So this looks nice and proper. Okay. So this is our position. Let's see of initial. Why is this? Yeah, you need to say, I promise, I solemnly vow that I will never change next to be something that is not first or second. But let's do this and then whatever we get for next. My console kinda broke. No, I don't want to migrate users or whatever. I want to run a debug on this. Well, we got something. So the multipliers are 1, 3, 4, 7, 6, 134, 136. Did we mess up? Yep, and nobody told me. This would have been fun to debug later. And this is why I'm trying it all the time, and I mean all the time. Basically, until your code is run, it's not correct. You don't know if it's correct. So that's it. So we all have the correct that the next one is second, and then 1367631. Okay, let's just console log the first object and see what we get. We started with 4 and 8. Let's go back to the Excel. So we have 4 and 8 and 0 and 0. Yeah, let's paste that all over the place. So if we run a 3, this will be 7, 7, 8, 8, 9, 9, 10, 10, 11, 1, 1, 2, 2, 3, 3. Yeah, let's do that. Actually, let's check all of them. And not just do this, but do this. Yeah, we're gonna use the fancy word iterator to log it. Not the state. Yeah, actually the state. That's the one that I'm interested in. I know that the second one goes next. Yeah, actually I get that. I don't get the multiplier, and we'll recheck. So we have 7, 8, 9, 10, 1, 2, 3. Yep, those are what we needed. So what we need to do now? Well, for each of these, we need to say this is a universe. Next to is next universes of the states. For each universe of next to, let's console log it. And just to know where we are, log me some lines, and let's run it here. So that there will be a relatively huge amount of input, so let's see it. Now we have basically all possible combination. The first one is 7711, 7722, and so on and so forth up to 7777. Combining everything with 8, with 10. Okay. So we need to find somehow how to loop. Of course we can nest 17 for loops one inside the other. But I have a feeling there might be a better solution. So we are getting I'm not gonna call this next universe, I will just call this universe, and the initial thing will actually be a universe. With a multiplier of 1 and this as the state. And I will make a nice little recursive method where what we do to return, find the player that wins in more universes. In how many universes does that player win? I am about 99% sure that the first player will win in more universes, just because he goes first. It kind of makes sense. Because it's 21. If you roll 9 and 8, doesn't matter what the other guy rolls, you're gonna win. Yeah, it's going up to 21. I would say that the average game would run something like 7 or 8 moves. Tops. Total. So 7 or 8 moves for the both of them, not just... So we're gonna have a universe, and we're gonna say for this universe count the wins. And this will return an object that kind of says is like this. First is number and second is number. So it's simple. If the universes dot state dot first dot score is bigger or equal to 21, let's check that. The game now ends when either player scores reaches at least 21. So 21 is a winnable number. We don't have to get to 22. So if the score of the first guy is more than or equal to 21, well, we return, yeah, this. In this universe, this guy wins. Doesn't matter how many universes there are, he wins in all of them. Yeah, if the first didn't win, then the second wins. We'd have no scenario when both of them reach above 21 at the same time, because we're not waiting for the second one to play and then to have some kind of a die-off. No, at the moment when the first reaches 21, we're done. So now we have the weird case. So if this universe is not a winning universe, neither the first one won or the second one won, then basically we need to get the next universes. Yeah, get all the next universes for the state. And yep, and I think this code will write itself for me. Yeah, we're gonna recurse on each of those universes, and nope, this is wrong, and I will fix it. So we will count who wins, and this will return a number that is either whoever won, and that will actually, we will need to multiply this by the number of universes. Yeah, because this will determine, for example, that for the first scenario, when the player draws a 3, it will determine that it will, or for the second scenario, for the 3 cases, we will determine that the first one wins 3 times and the second one wins 0 times. But if our own universe's multiplier is 20, then that means that we have a 60 wins for the first one. 20 times 3. So now we can just say this, I guess, and the rest will be simple. If wins.first is bigger than wins.second, return wins.first, else return wins.second. And I have a feeling that this won't run immediately. Let's start it and let's let it run at least for a minute or two. The bad thing about deeply recursive calls like this is that you have no idea whether this thing is running or not. But fortunately this one actually finished and it returned a number. Let's see if that number is the correct number. That's great. So we have a runtime of 14 seconds. That's amazing. So we just need to put our own numbers and hope that this is not some happy case for the 40 and we have a pathological case for an input where it will run and run and run and run. Yeah, we'll wait. Let's say we wait for a couple of minutes and we got another number. In this many universes our guy wins. Let's see. And that's the correct answer. And we got it in just 12 seconds, which is not bad. Let's return to our advent calendar, but I want to try something more. I want to count first. I want to count how many times this call got called. And I will just do this. Yeah, just increase this by 1. There are better ways to do it, but this is a quick and dirty. Because that's the problem with recursion. You have no idea. Each singular call will be fast as heck. But the problem is that there are so many of them that they are problematic. So we're not gonna return after this. We will just count wins was called, yeah, that much times. So this method was called this many times. And this is still, you can say, yeah, this is much smaller than the numbers we got as the result. but still it's one of those numbers when we need to actually add dots to be sure of the magnitude. So we only got around 110 million calls. Yeah, trivial. And 12 seconds. So we had 109 million function calls, and I guess the stack got as deep as 17 or 18. That's not a problem, but this was incredibly wide because each call of accountants actually calls this 7 times for our 7 options. So we have a 7 fan out factor. So after on the second level there will be 49, and we actually had these numbers here. So most of them will start to fizzle out. For example, the situation when we throw a 9 and an 8 and anything else basically will end here. So this number will be much lower, and so on and so forth. And I guess we will get up to right about here. We can also count that if we want. We can add a level parameter, for example. Yeah, let's do that. Let's do that. This is a solved task, so we just want to enjoy our development a bit. So and to be honest, since I'm doing this, I will most very likely use this video as a primer for how to debug and how to analyze recursion sometimes later. So, full disclosure, I'm gonna abuse this task. So let's create basically a hash or something like this, level calls, and this is gonna be an array of, yeah, let's just do this. It's filled with zeros, and we're gonna add a level parameter, which is a number, which by default will equal 0. So we don't need to specify it. In addition to count calls, we will add this. Say that you got called on this level. And of course, level +1. So this will give us a nice little table of level calls. And I'm gonna use the console table call here. It's gonna give us a nice little table of how things went and how many calls we got on each level. And no, it's gonna be ugly because it's gonna have a bunch of zeros, so I forgot to do this. Yeah, this copilot thing it's going towards scary. It still hasn't solved any of the tasks for me, but it does do good work. So we can see how it goes. So the maximum number of maximum level of recursion actually got to 19. So there was a case that I didn't analyze too well when we had 19 moves. And you can see that it's kind of spindle shaped, and there were 22 millions on levels 11 through 13, and then it's about half each way. But you can see that these are the levels where we are still not able to finish the game, so that will match actually with our table. So first was 7, then 49 after the second move, 343, 2401, 16807, and as I said, because some of the games will finish on the 5th move, this one is lower than our straightforward number. So these are the maximum numbers that can appear on that stage. And for example, if we left that the winning number is 1000, this they would have been like this, because for a 1000 the minimum number of games that you can, or runs that you can play, even if you're able to get constant tens, you will need 100, 200 moves actually, because you're moving and the second guy moves. So this would have been correct up to 7 to the 200 degree, and I don't think there's that many atoms in the universe. So you can see that each of the calls, so we managed to actually do this many calls. Let's do a little bit of calculation. We managed to do this many calls in 12,569 milliseconds. The other way around. So basically we got 8,000 calls per millisecond. So each millisecond we got 8,000 calls. Yeah, this is how long each call took, but let's divide this by 1,000 actually. So we got about 8 calls a microsecond. Basically, one call of the countwins function lasted around 100 nanoseconds, which is quite a short time actually, if you think about it. In 100 nanoseconds the light can, that's longer than what the light goes from the ground to your eyes. If you're somewhere on the 100 nanoseconds, or 1 nanosecond is about that much, so about a foot, so 100 nanoseconds is 100 feet, 30 meters in real measurements. Anyway, yeah, this looks fast, but is it fast enough? So what works really well with recursion, especially this kind of recursion, is something that is called memoization. So, because we have just 4 numbers, and I already analyzed that part, that we don't care how we got here. If this is the same thing that we already had, it will, from here on, will run exactly the same. So if we have two different, so we might have a case when the first guy threw 3, then 4, and then 4, and the second guy, yeah, let's have them throw the same. So the first guy threw 3, and the second guy threw 4, then the first guy threw 5, and the second guy threw 6. That's okay. And then but this is completely equivalent with this situation. The first guy threw 5 and 6, and then they threw 3 and 4. Yeah, let's go to the positions actually. So the first one ended on position 3 and then on position 7. And the second one was on position 1 and went on position 4, let's say. Okay, I'm getting messed up, but you get the point. It doesn't matter, there could be possible ways when we can get to the exact same situation, the same number of points and the same position. And to be honest, yeah, let's calculate that. Because how many possible states there are? Because we had something like 108 million calls of this method. Do we have more than 108 million possible values? So this can have any value between 0 and 20. So that has 20 different options. This also has 20 different options. This has only 10 different options. The position can be 0 to 10. Yeah, let's include 21. Let's be generous. This has also 10 different options, and this one has 2 different options. If you multiply all of those together, so basically all of this is independent. Not really, some of these are invalid, because for example this cannot be 0 while this is on the other foot. The first one cannot get 0 options. But even allowing for all the possible scenarios, we have less than 88,000 options. And if I'm not mistaken, 88,000 is a bit less than 109 million, which means that some of these calls were exactly the same. There are just 88,000 possible universes, and we made 109 million calls on them. So what I'm gonna do is I'm gonna trade speed for memory, so to say. So each time I'm calling a method, I'm gonna define a cache, and that cache will be a map would work just as well, but I'm gonna use something like this, even simpler. Yeah, a string hash is basically a type I've defined, which is an object that has keys that are strings and values that are strings, and actually it's not gonna be a string hash, it's gonna be a hash of number. It's gonna have values which are strings, keys that are strings and values that are numbers. So what I will do, each time this thing is called, I will calculate the key from the universe's state. If that key appears in the cache, then we already know what is the the response should be, because for this state it's that much, and I'm just gonna calculate it based on the state. I'm just ignoring the multiplier. We can have 7 different multipliers, but even if we include that this can have 7 different multipliers, I'm still quite convinced that this is less than 109 million. So we have something like 600,000 different options, but the multiplier is external to this. It doesn't matter, because each universe that comes into this position can have this value, will have this value exactly. Doesn't matter if the multiplier was 1 or 7. So if we have that key for that state, we just need to return basically the universe multiplier times the state. Okay, the result is not that, the result is this. It's not gonna be a hash of numbers, it's gonna be a hash of these. And we cannot multiply those by the multiplier, so we will need to have a bit more complicated code, but not too much. We can cache these, so we can cache also these values when we are returning them, but actually let's do that. So instead of just returning this, we'll just do this. This is the result, and set the cache's key of this result to this. So next time we're not even getting to this part, we're just returning from the lookup. And we just need to use this value. So the first one is the 0, the second one is not. Actually, I will remove this. Yep. And I will return this. So the multiplier is only applied at the end. It's gonna be off because this shouldn't be. We're wrong here because we are using the multiplier. Now the multiplier we already said is not important. What we need to do here is first is 1 and second is 0. Yep. It will be easier to redo that work. So this is not the multiplier, this is 1. And we don't need to assign it to anything, we can just set it. Bam. Let's see how this pans out. Don't forget, one of the things that we need to achieve is return the same value. It doesn't matter if our code is a zillion times faster if we are not returning the correct value. Yeah. If you want really fast code that returns an incorrect value, you can just use random. But I want to have the correct value, and I want it to run a bit less times. Yeah, the value is correct. And let's see once more the timing. This took us 232 milliseconds. And we had 188,000 calls. So we still called in it, and we're counting the duplicates calls as well. We're counting the calls that ended with a cache lookup. If we add this code here, how many times we actually had to continue in the processing and didn't end with the cache lookup, I think you'll see that the maximum times we called the level what we'll get was 15, and we actually got 39,000 different combinations. So this method was called with 39,000 different parameters, so to say, different keys. But the total number of calls overall was just 188, which again is a bit less than 109 million. And of course it ran a bit faster. So we don't actually need this, those were just diagnostics. Let's comment them out. As always, I don't mention this enough, but as always the code will be available on my GitHub account. You can take a look at it, and npm run all to see everything that I've written so far except task 19. which will have a specific another video on optimizing that one. You can see that right now this just takes about 4% of my total execution time, and the total time that we have is something like 4 seconds, 4 milliseconds, 4 seconds, which I'm fine with. So bye for now, and talk to you tomorrow for the day 22.